Video, we're going to explore connecting batteries in series and parallel. We'll also examine one of the dangers associated with connecting batteries in parallel. For our discussion, we're going to assume a particular battery. In this case, we're going to talk about the lead-acid PB5-12 battery. This is also equivalent to an NP5-12 battery. It has a weight of about 4 pounds, which is equal to 1,800 grams. It has a nominal voltage of 12 volts DC, a capacity of 5.0 amp hours when measured at a 20-hour rate, and it has an internal resistance of 27 milliohms. This is a fairly common battery. You'll find them in small UPSs or children's toys. To better understand these specifications, let's first look at what we mean by capacity. Here we see a curve where we have time on the horizontal and voltage on the vertical axis. And when you first connect the battery up to a load, what will happen is there will be an initial voltage drop, and then the battery voltage will maintain fairly constant for a period of time, and then it will start to drop at the end. So here we say that 12 volts is the nominal voltage of the battery. That's where it stays for most of its life. And we reach this point here down at 10.5 volts, and we say this is the discharge point for the battery. Now, for the battery that we chose, it was specified as 5 amp hours at 20-hour rate. In theory, that battery could give you 5 amps for 1 hour, or it could give you 2.5 amps for 2 hours, or 1 amp for 5 hours, or as the datasheet actually says, 0.25 amps for 20 hours. You'll see that each case the product is 5 amp hours, but this is the specification that's listed in the datasheet. We could go on to talk about why you get less energy out of the battery as you move this way on the chart, and perhaps we can do that on another day. Anyway, back to this curve here. This line was generated by connecting up a load that consumed 0.25 amps, and the amount of time it did that from here to here was 20 hours. Next, let's look at the model of the battery. So our battery, well, at first glance it's a black box. All we know is that it has a positive terminal and a negative terminal. But we can model this as an internal resistance in series with an ideal voltage source, like so. This resistor came from the data sheet. It has a resistance of 27 milliohms, and this power supply has 12 volts DC. You may recognize this as the Thevenin equivalent circuit. Thevenin equivalent. Okay. And with that, we have an ideal voltage source connected in series with a resistor. So with this in mind, we can now explore what it means to connect batteries in series and in parallel. So let's say you needed a 36-volt power supply. You could connect 3 batteries in series like so. Where each resistor here is 27 milliohms, and each ideal voltage source is 12 volts DC. When you do that, this is the equivalent of saying a single 36-volt power supply in series with a resistor. We can do a quick calculation to figure out what the resistor is. You'll notice that all of them are in series, so the equivalent resistance is equal to 27 plus 27 plus 27 milliohms, or 81 milliohms. Now something to notice is that the current is the same for this entire circuit. So now when we specify the amp hour rating of this battery, we would say that this is a 36 volt DC battery with a 5 amp hour rating. This will make a little more sense when we get to the parallel connections, so just hold tight. Oh, one more thing. Why would we connect batteries in series? Because we need the higher voltage. And we see by connecting the 3 batteries here, we've gotten the higher voltage we desired. Moving on to parallel connections. Why would you parallel batteries? Well, higher current. We'll connect parallel batteries like so. So here we have our series resistance. Here we have our 3 batteries. Again, each resistance was 27 milliohms. And each source had a nominal 12 volt DC. Now, something you could do at this point if you wanted is you could think of these as the same point. And if you wanted, you could connect these together. That is a valid thing to do with with ideal voltage power supplies, provided that they all have the same voltage. So when we're done, we could model this as a single 12 volt DC power supply in series with the resistance. Now we just need to figure out what that resistance is. So Req is equal to 1 over, you'll recognize this is the formula for calculating parallel resistors. Oh, excuse me. 1 over 27 milliohms plus 1 over 27 milliohms plus 1 over 27 milliohms. And when you do that, you'll end up with 9 milliohms. This is the equivalent circuit. Now, back to the amp hour rating, you would call this device a 15 amp hour battery. The reason is because you have the current out here, so we'll say I out. And if you look at each individual battery, it's only providing 1/3 of that as the batteries work together. Okay. Again, 15 amp hour battery. Moving on, let's talk about the dangers of paralleling batteries. And for this discussion, let's assume that you've done something silly, like connect a 6 volt battery in parallel with a 12 volt battery. So we'll keep our PB512 battery, which you recall had a 27 milliohm resistance and a nominal 12 volt DC voltage source. And we're going to connect this up with a PB5-6, which is a slightly smaller 6 volt battery. Oops. Okay. Again, it has 6 volt DC, and this particular battery has 13.5 milliohm resistance. And just to make things a little more interesting, let's connect them using real wire. So in each case, we'll assume that this is 6 inches and another 6 inches of 16 gauge wire, which gives you a resistance of about 2 milliohms. So there we are. We have our 2 batteries. Battery 1, battery 2. The 12 volt battery is a PB5-12. The 6 volt battery is a smaller PB5-6. And these are the resistances and the voltage, including 1 foot of wire, so 6 inches up here and 6 inches down here. Now, when we do this, we can make an equivalent circuit, and that would look like this. We would have our 12 volt battery, a series resistance, like so, and this represents the 6 volt, So 12 volts here and 6 volts here. And now this resistor here has a value of 27 milliohms plus 13.5 milliohms plus 2 milliohms plus 2 milliohms, representing the internal resistance of the 12-volt battery, the 6-volt battery, and the wire. And when you do that, we can say that the resistance is equal to, let's see, 44.5 milliohms. Now, using Ohm's law, we can calculate how much current will flow. So current is equal to voltage divided by resistance. In this case, the resistor will see the difference between these two power supplies. So it'll see 12 minus 6 volts. And the resistance, we said, was 44.5 milliohms, yielding 135 amps. We could finish there and say that's a lot of current, but it might be useful to explore how much power is being dissipated by the system. So you recall power is equal to voltage times current. And here we have a 6-volt difference, and the current is equal to, we said, 135 amps. That gives you 809 watts. We could go one step further, knowing that power is equal to I squared R. I won't show you all the calculations, but we can calculate that there is 490 watts being dissipated in the 12-volt battery. There is 73 watts being dissipated in the wires, and there is 245 watts approximately in the 6-volt battery. Now, this is a tremendous amount of power, especially this one here and this one. That's roughly equivalent to a small space heater. Know that the battery has no cooling mechanism, and it's going to get very hot. Hydrogen and oxygen gas are going to be liberated, and it's quite likely that the battery could have an explosion. So remember, always wear your acid-resistant safety goggles when you're experimenting with lead-acid batteries.